I almost finished actually, so I just can't come back really briefly to this story of non-statement view, and should be V there. And I think that this standard non-statement view, as I told what Patrick Supes and others tried to do, actually the idea was the thesis of this non-statement, once again, was that theory is not set of propositions, but is a class of models. That was their idea. But as models, they would, at least Patrick Supes would use Tarski notion of models, set theoretic models, and this Bourbaki style of presentation. And I think it really did not give something radically new, right? So of course it was never used, say, in science for scientific purposes. It's rather remained kind of philosophical project which allows one perhaps kind of find kind of structure of knowledge, structure of theories, how certain theories relate to certain other theories, that kind of things. But of course it does not give you this concept of model in a sense in which physicists say, or engineers would be satisfied. And I think the reason is that they, after all, they use the same axiomatic method. There is no new idea. They rather stress the semantic part of standard axiomatic method. They say that the principal concept of logical inference should be semantic consequence rather than anything syntactic, this kind of thing. But basically it remains the same technique. While if we use this homotopy type theory, if we consider it in that context, right? So homotopy type theory, and what I try to generalize by calling it constructive axiomatic method, just gives you precise sense in which theory does not reduce to set of its propositions. So it contains its set of propositions, but it's not the whole thing. So you have this further higher order structure, which you may, look, it's a long discussion, I only point to it now. You may say it's not propositional knowledge, it's otherwise called knowledge how, right? So we have this knowledge formalized in the form of rules, and only part of these rules, which are logical rules in narrow sense of being rules about how to infer propositions from other propositions, right? And I think that that's also may bring sunlight to that discussion in epistemology. Of course, there is a sense in which knowledge how may be in some meta language given a propositional form, but I don't think it's an important issue. It's important to observe exactly that typical scientific theory is simply not, it's not reduced to this propositional form. It has this non-propositional part, and there is nothing opaque or informal in this non-propositional part, as people often tend to think. It's also formalizable, but formalizable not in propositional terms, but in forms of rules of applying, I would say, to objects, and other people may perhaps call this structure, but actually why I call it objects, one reason is that I try to connect it in this early discussion, we say objections. This is from Grassier's paper of 1907, which is called Kant and New Mathematics, and this is his reaction to Russell's principles of mathematics. And then he says that this kind of logically based approach he calls logistics, and so he says that from the standpoint of logistics, which is Russell's project, but I think it more broadly, of course, Hilbert and Russell a different project, right? We don't call what Hilbert proposed a logicism. It was not about reducing mathematics to logic, but still there was this idea that logic is fundamental. And so I think this remark applies to Hilbert project too, at least partly. So he says, the task of thought ends when it manages to establish a strict deductive link between all its constructions and productions, construct production of thought. the worry about laws governing the world of object is left wholly to the direct observation, which alone, with its proper very narrow limits, is supposed to tell us whether we find here certain rules or a pure chaos. So he points out that there is, in such a setting, there is no rules for objects. There is only rules for propositions. And there are some objects, but they are kind of packed into propositions, into propositional semantics. And there is no constructive rules for objects themselves. And according to Russell, logic and mathematics deal only with the order of concepts and should not care about the order or disorder of objects. As long as one follows this line of conceptual analysis, the empirical entity always escapes one rational understanding. The more mathematical deduction demonstrates us its virtue and its power, the less we can understand the future role of deduction in the theoretical nature of sciences. So it's what later was called Wigner problem, right? How this abstract mathematics applies to real world and life. And of course, Kasirov somehow thinks about this Kantian answer to this problem, but he really makes, I think, very significant effort to modernize it completely. He's not at all orthodox Kantian, and I think what, at least again, this homotopy type theory just does what he wants here, right? We, in addition to rules of deduction in this narrow sense, we have there these rules for object, right? And I just and here is Levier. He is inspired not by Kant, as Kasirov, but by Hegel. But I think it's still the common, how to say, problematic when he says experience with is from the same introduction I already quoted. Experience with sheaves, etc., shows that the set theory for geometry should apply not only to abstract sets divorced from time, space, ring of definition, etc., but also to more general sets which do in fact develop along such parameters. So you see, he aims to this logic be somehow part of our natural sciences, our construction of physical space and so forth. And that's, I particularly like this phrase, Kasirov. Here he just says in 1907 what is important remains of Kant, why we should not, after Russell, just forget about Kant, because what he says is the most important issue, just we forget all these details about Euclidean or Euclidean geometry, whatever. He says logical and mathematical concepts must no longer, means after Kant, no longer produce instruments for building metaphysical order of thought, and their proper function, their proper application is within empirical science. And that's, of course, that Russell would not agree, and all this construction of mathematics in Russell and also with Hilbert, I think that is a common point, is that mathematics becomes kind of construction of, say, metaphysical world or possible world, however you call them, which have no direct link to physics, and some people would praise this. They would say that's how mathematics should work, right? They would consider as a great achievement that, say, geometry forgets about its links with nature, becomes kind of speculation. We may have different spaces, but I think Kasirov's project is just to keep mathematics centered on empirical science without, of course, giving up these new achievements, without, it's no question to come back to Euclid or something like that in that project. So I think that homotopy type theory, Topos theory, Levier just point to similar direction, and that is at least interesting project. Of course, there is many philosophical issues to discuss about it. I don't have, but I just want to finish to pointing to what I think is really open problem, and it's problem both conceptually and technically and mathematically, is this. So it looks like we may use tentatively, at least, and I try to do this with my other talk in Cabrera seminars, how we may use homotopy type theory for modeling, for providing something like mathematical models in, say, physics. And of course, since it is geometry, it looks much more like modeling in physicist sense than, say, the star-scaling of modeling, right? Which is very, how to say, separated from what is people call by modeling, talking about, I don't know, computing models of climate and things like this, right? Even if Patrick Supis, he insists that this Tarskian notion of model actually, with all these differences, may work for science, but I don't think that's really, I don't think it's really made justice to their own this non-statement view, after all, right? But problem is that I think that roughly model theory of homotopy type theory, because what we call this homotopical interpretation is not really a model in anything like strict sense, Tarskian or any other, right? And here I think there is, for example, this controversy between Vladimir Voevodsky and Steve Audi about modeling of homotopy type theory, because Steve claims he knows how to model it in abstract homotopy type theory, that means that will is category, and Vladimir Voevodsky says it's just wrong. He just says he has counterexample. He makes more specific model in simplicial sets, which is homotopy category, but it's not general homotopy, it's still specific homotopy category. And apparently they simply disagree what counts as a model in cases. It's not about technical details, but just there is some conceptual disagreement here. And indeed, we cannot use the Tarskian definition of model straightforwardly, at least if we think about homotopy type theory in the way I just proposed, right? That it's not all propositional. Then how we define the satisfaction relation, right? Because typically, and even in Topos theory, in this Kripke-Girial semantics, satisfaction is defined through truth value, right? We say that we get certain true proposition at the end, and that means that certain formula is satisfied by certain semantics. And here, if the thing is not propositional, we should use something else. And there are further, actually there are some concept of models which are not kind of officially declared, I think, but which are used. For example, this idea of initial model. That model should be initial category in some broader categories. In that sense, generate this whole category. And it's not, of course, in Tarski. Some people, I think, use it as a matter of. There is a book called something like categorical model theory, and then you find a lot of these things. But I think all this really needs kind of conceptual clarification and development. So I think that my next project to really describe what wouldn't be a model. So I come to conclusion. So what we see in these two lectures, first thing that this, what I try to describe as constructive axiomatic architecture, is rooted in history, like Euclid, and also it's found in this more recent practice, like elementary Topos theory and homotopy type theory. And in this setting, we find a very different pattern of relationship between logic and geometry, different from what is assumed in received axiomatic method. And I would like to stress in the received axiomatic method, we, as I told, we fix this logic with logical semantics, of course, and then we add axioms which has no direct, how to say, link with these logical principles, right? We just use this logic for everything, for doing set theory, for doing Euclidean geometry, for saying that Socrates is mortal or something of the sort, right? And there is no, say, direct link between this logical structure and geometrical structure. While here we actually discover this link. I think, in a sense, Hegel and Louis are right. It's somehow there. We may show that. And so this alternative architecture just is supposed to exploit this link. And actually, I think it's when we do theory, kind of axiomatic geometry in this Hilbert style or Tarski style setting, we think about geometry as kind of, how to say, we make a formal theory, but which is become contextual when it filled with kind of intuition of kind of content, right? While I think there are serious reasons to take, we are saying that logic is a formal and provides a logical form, right? But geometry is also formal science, right? So we may probably distinguish and somehow balance logical form and geometrical form. Not saying geometry is kind of content, which is broad, which is, how to say, managed by logical means, but it's also a form. And so this picture of logic being part of geometry just says there is something more general like geometrical form, and logical form is a particular element of that. Maybe more universal indeed, and so on. But that's a different picture, which of course needs further analysis. Right. And I think it's also important, if we're talking about this practical problem of bringing, say, logical methods into science, as I already mentioned, this received axiomatic method during 100 years of systematic efforts has rather poor performance, I would say, except this theoretical methodological part where important mathematical results were achieved. While this constructive axiomatic method in the form of homotopy type theory already today, no, first of all, if we really count Euclid and also by Hilbert and Bernay's suggestions, we qualify as axiomatic theories like Newton's and Clause's, so there is kind of historical proof that it works in science, unlike this more specific Hilbert-style method. And already today, homotopy type theory already performs something, right? We have this proof assistants like Koch, which already today effectively used in mathematics. This four-column theory proof was rewritten by Thierry Coquin in the 90s using Koch, and that's really works. So there is really, I think, reason to be enthusiastic about that, and in any event it's worth trying. So I think.
Okay, so the floor is open for discussion. Comment, question?
Yeah, could you get back to the slide where you mentioned Cassirer and the two ones before? Yeah, the one before, and yeah. So I've just, a couple of questions. First, when you say it's not propositional knowledge, any type is viewed as a proposition. So in
no.
Why not?
Once again, I think we already discussed it, but my understanding, what we should understand, this cumulative character of this hierarchy of types, cumulative, right?
Yeah.
Of course, if you truncate type to this propositional level, it is proposition. Also, if we make this kind of slice, right? Okay, we have a path space, and that path space is a type, right? And it is a proposition if we kind of slice it. But if we take, path space together with this underlying point space, which makes sense. In a sense, it makes no sense to talk about paths, forgetting that it passes between points. So the talk of paths somehow needs talking of points. And so now we have this two-level structure, at least two levels, right?
Yeah.
Points and paths, right?
But
and this is a homotopy type,
yeah,
right? And it is not propositional type.
Yeah, but it's it's a words. Because in Martinov's conception.
Right, that was not. What I'm saying now was not in Martinov's conception, I agree.
Yeah, but you cannot say that homotopy type theory is based on Martinov's type theory, and that in fact homotopy type theory does not retain the basic tenets of Martinov's type theory, which is that higher propositions, so to speak, are propositions. That's the whole view of Mathematical type theory. So, I mean, you could say, well, you could defend your view, but it's highly contentious because the main point of homotopy type theory is that there are several orders of propositions, but higher order propositions, if you want to call them this way, are propositions.
Look, Brice, I think we are really talking about different orderings now. Because Martin Löw, he simply, that structure that I'm talking about, he didn't know about that. Nobody knew about that before Streicher made this groupoid model when they just distinguished two levels, and nobody knew about further structure before.
Identity types are propositions in Martin Löw.
Of course they are.
Ah, okay, and so there should be at the first level, not the basic level, in your view.
Now, look, once again, the trick is to take not just propositional type of, that's what I would call slicing, you know? You just slice your, say, identity type, and you're right, no matter in which place, maybe very high order. And of course, if you slice it, of course it is again a proposition. But trick is not slicing it, but making thick. You see? And then it's not. And that's something that Martin Löw did not intend to do. He didn't know about that. Nobody knew about that before Streicher, before the homotopy.
I might intervene because I had exactly the same remark as Brice. I think it might be because of the way you tend to present what a proposition is, which is, if I understand well, something that is just has a Boolean value, which is a very poor notion of proposition, even for the 20th century. You know, from Gensen on, I would say. So, I mean, I agree with Brice with the idea that the propositions are of different types, and that was also the case already from, I don't know, from Frege on, you know? You have propositions that are from first type, second type, there are propositions about propositions, and propositions about propositions about propositions, and these are of different types, high order propositions. And the problem is, are these high order propositions of the Boolean type? And that might be a problem. That was one of the problems of Frege, that thinking that all propositions, because of being propositions, they are giving you a truth value. But if you get into the proof theoretic framework, propositions are not seen that way any longer. And propositions are just, I would say, like settings in which internal logic interact. I mean, they are seen like that. We've seen here Girard present a theory in which individuals are propositions of a very particular type. That was his idea.
Which text you referred to?
He was inventing that at that particular point, but I can quote it to you. The so-called individuals, they are nothing else than propositions of a type, very restricted type, namely the multiplicative connectors. So, in the tradition of the proof theory, propositions are not just the subject predicate or the first order logic functional framework that just takes either objects or Boolean values and gives you a Boolean value. And in that sense, I think I don't understand that much the way you're you're fighting so much propositions, whereas they are another framework in the case of proof theory, very much in symphony, which what you are presenting, and I think that can agree with what Brice was trying to say.
Now, look, I will say what I learned from Frege, and I'm also based on Zenon Bedeutung, which is later, right? It's a mature view. And then, of course, you know well, he says that all proposition has the same reference.
Yeah, of course, but that's not longer an issue afterwards.
No. Well, so in that, which is basically Boolean value, right? Truth. So in that sense, I think it's compatible. Of course, there is. I understand this worry, which is kind of impoverished concept of proposition limited, but it's in this homotopy book. It's called mere proposition.
Mm-hmm.
But I think it's still I would defend it. So if we talking about this framing ideas, right? So they all refer to the same things, all propositions. All right. So in that sense, it's compatible. So what is the difference? Is their sense, as Frege called it, right? He did not provide any formal system for senses, right? He did provide something for references, Begriffsschrift, and later development, but no formal theory of sense. He only points that such things exist, right? And so what I'm trying to do is in this Venus example, it's exactly reconstruct this difference of sense in terms of this higher order structure. So, no, right, here there is kind of issue, but it is at least partly terminological. So we may say this different of sense, right, it's this higher order structure, but it does not make part of proposition properly. No, I don't know. I agree that this concept of proposition is kind of limited.
Because when Carrick Howard are saying, or Howard particularly is saying, like the types as propositions, the propositions they are thinking about, they're not free-end propositions defined by the fact of value to value. And now they are more settings in which a certain interaction of a syntax can take place at both levels, either within this propositional connection, which is like A implies B, this is, I don't know how you call the symbol of Gensen thesis or I don't know what. B implies C, and that's kind of a proposition where some elements within have a certain relation, and then you have the relation of deduction.
No simple point. That's all this Frege logic, classical first logic, is truth function.
Yeah, of course, but
that's it.
I think that the idea is that it's not what is happening when what they are thinking type as propositions. They are not talking about those propositions. They are not talking like propositions in the Gensen style, which the meaning, like informal meaning of this idea of proposition is not the same as that. I think, I know.
But Gensen style is not axiomatic in the sense of Hilbert. If I understood what André wanted to show is that you have Hilbert style of axiomatic, here you have another style, and it's different. At the time of Hilbert, you have Gensen style, which is opposed to axiomatic Hilbert style.
In a sense, it's closer to Gensen style. I say why? Because, say, in Martin.
What is closer?
Say, Homotopy or Martin Luther.
That's what you're saying. Yeah, exactly.
But I mean, it's well known. I mean, there is an opposition between Hilbert style with axiom, formal system, and so on. And
the problem is just trying to like two things there. One is the problem is to call proposition within the framework of the homotopy type theory something that is not what they are calling propositions in the case of type as proposition. Because I think it's not longer the case, even if there are links there. But there you can have like higher order propositions. That's one thing. And the other thing is that the inspiration of Gensen is, in some sense, Hilbertian, even if it's not this axiomatic style of Hilbert, which is intended. But the idea of a proof theory is ready in the idea of mathematics of Hilbert. So. In some sense, there are two regions of Hilbert. Either you read like very model theoretically.
No, look, I think you cross purposes because there are different proof theories, right? That is based on kind of instantianistic constructive proof theory. And of course, what Hilbert calls proof theory is very different, right? It needs this distinction of meta mathematics and kind of objective mathematics. And here there is no such distinction. That's the thing. Right.
Yeah, but I still think that there's some Hilbertian heavy inspiration in Gensen in some sense. I mean that what
inspiration,
Hilbertian inspiration within Gensen.
Right.
which of course is not the axiomatic part of it, but it's more the interactional part of it, which was already in Hilbert too. So if you reduce Hilbert to the axiomatic part, then you reduce the idea of proposition to truth value expression. Okay, that holds, but I think you can have a notion of proposition in the other sense, which would solve this kind of problems, you know, in which a proposition is not defined by its truth value, but more by the interactions it can give form to within a interactive set.
No, but here all these interactions, if you like, they are kept because we may also derive. You mean how this proposition is derivable from some other proposition?
No, but I mean proofs go are how do I say are instantiated in propositions. The proof, the internal logic one wants to make appear. You make it appear out of interaction between propositions. So propositions are not the basic element, but are the basic setting in which the interaction can appear. And if you just shift the notion of proposition from this just truth value thing to a setting for a
but the very important difference between, even I try to make an analogy, of course, fundamental difference between Topos theory and Homotopy Type theory, that in Topos theory we have this internal truth evaluation, and in Homotopy Type theory we have no such thing, right? So it's actually, it's a different idea of being true, of course, intuitionistic.
Yeah, I'm just pointing out that there might be two different kind of ways of dealing of thinking what a proposition is, and if you just take one, you are forced to say that the other position has nothing to do with propositions, whereas in fact they have. It's just that the proposition is something else for them. But that's just, I think that.
No, but I mean, it's just that you are jumping on the word of proposition. I mean, the point was that you have a certain view of axiomatic, in which you isolate a certain number of statements.
Yeah, of course.
And you say that we derive from this statement the other statement from the theory. This is what we call Hilbert system. I mean, even today, formal system a la Hilbert. Then we can talk about position, Hilbertian inspiration.
No, but I think the point was about propositions. I agree with you, but the point was about propositions.
I mean, the slide was about distinguishing between propositional knowledge and knowledge how.
Yeah, but I did not develop this.
So I don't understand, because knowledge how is practical knowledge. I mean, that makes sense in the sense.
My point is that's wrong. That's
no, I mean, you cannot take it as obvious, because when you, I mean, all the literature about knowledge, about knowing how, is about knowing how to ride a bike, knowing how to follow a recipe, how, I mean, it's practical knowledge. And the point of that literature is that there is knowledge within practical realm. I mean, within the practical realm, there is knowledge involved in riding a bike. There is knowledge in, and so on. So, if you speak of that, that is what you are referring to. So if you apply that notion, which is with all its undertones, to the case of homotopy type theory, it does not make sense. I mean, to me, I don't see how it is. How?
Perhaps I did not have to mention it because you're right, it's a big issue. But my argument, my view is that it's actually it's a wrong perception of knowing how after examples like you just mentioned, right? And so my claim is this non-propositional knowing how. First, it is formalizable. Just let me finish. In terms of precise formal rules, right? And second, it is fundamental for theoretical knowledge. It's no specific relation to buying a bike or something. And by the way, remark that logic, like logical knowledge should be made, right? it is knowing how, right? A particular method. So we may get rid in a logical system of axioms, right, of tautologies, but we cannot get rid of rules.
Okay, and if I understand well, what your claim is that these rules you cannot, you cannot fully present in a propositional form. That's your point? Because
no, you may, but it doesn't lead you anywhere.
Yeah, that was what I was trying to say. I mean, you cannot account for these rules in a propositional axiomatic system. That's your point?
No, the point is that in a standard axiomatic system, you do have rules, right?
Mm-hmm.
But the only type of rules that we have,
Mm-hmm.
they are rule of inference,
Mm-hmm.
in a narrow sense of rules of how to obtain propositions from certain other propositions,
Yeah.
right? My claim is that for typical scientific theory, right, this is not sufficient. That in typical scientific theory, we also need rules for objects, right? That was Cassirer's work, right? Or it's what Kant did more or less, right? So in addition to these rules for propositions, rules of inference, we need further rules, or perhaps like in homotopy type theory, more general rules which apply across the type distinctions, right? So that's the thing. And that's I think about this as knowledge how.
Okay, I would like to address your slide on Cassirer, but then before, just one thing. Could you give me an example of a rule about how? About that instantiates knowing how in homotopy type theory, for instance. What is a rule of that kind?
It's rules for forming types. For example, if we have I don't know, type A and B, right? How it's right. We may make a new type, which is dependent type, right? How it writes, maybe remember better. So I have X in A, right? And now I
B sub X,
B
sub X, or B of X. Type is a type.
Is a type, right?
Yeah.
That's the rule, and this is formation rules, right?
Yeah. So this is a knowing how.
Yeah, that's
But you have that in.
No, I guess what now have we have make separate.
No, I mean it's in that case. I mean you have that even in Hilbert. I mean, you have
No, except Hilbert, and that's what Cassirer points to, and quite rightly, that in Hilbert, just like in Russell, in that respect, there is no difference. These people just reduce all this rule to rule of inference, and that is not justified, I think.
Okay, so now I have a question about Cassirer because I don't understand at all. I mean, I really don't understand. I mean, Cassirer, at least maybe you too. I mean, first, it's what are the objects that are considered?
Yeah.
The Principles of Mathematics, Russell's book, is about mathematics. Okay, it's not about experience. It's about mathematics. So, of course, the Principles of Mathematics does not mention experience and empirical objects, but
It's not.
I mean, and in fact, it's not expected to mention an empirical object. It's not the point. And okay, so I don't understand why experience objects should be mentioned. There is some kind of confusion about what an object is. Okay, you have objects in a theoretical framework, in mathematics and logic, and you have objects in empirical sciences. It's not the same thing.
No, he does say the same thing, but in his conception of mathematics, which is Kantian, broadly speaking, right? He thinks of mathematics as, if you like, part of empirical science, right? He says it's just a wrong idea to make some metaphysics.
Yeah. Okay, so it's completely outdated, first, and second, I don't see the point with the connection with the homotopy type theory. I mean, homotopy theory has nothing to do with experience and empirical objects of any kind. It's just a purely theoretical framework.
You know that
I'm trying to put a lot of things together, that's true, but no, at least it's the view that you express now. It's not shared by everyone. My professor was Vladimir Arnold, who, maybe just claimed mathematics is a part of physics. physics, and the most trivial one, and logic is a part of mathematics, and the most.
Yeah.
So I find at least this view interesting and defendable. And I just don't buy this. This is metaphysics. It's not disagreement. Is not about mathematics. It's metaphysics. You just postulate that mathematics is kind of abstract.
Anyway, about Russell, it's completely false because Russell was the one who made an important progress about formalizing experience and empirical perceptual experience and so on. So I mean. It's a confusion between Hilbert and Russell. It has nothing to do, and Russell, applied logic to the formalization of perceptual knowledge, experience, physics. There's a paper from 1912 entitled "On the relation between on the connection between sense data and physics," and it's about reconstructing the visual perceptual space with the formal tools of logic. So, I mean, if you mention Russell, then, or Cassirer, and then it's faithful to what Russell did.
And I should make
Don't touch
separate
It's completely schematic, oversimplified, and inaccurate. Completely. And anyway, beside that, it's not very important, but I don't see the point with homotopy type theory.
I explain that. Okay.
The Kantian empirical phenomenological thing has nothing to do with the homotopy.
You are right, of course, that to defend it more seriously, I would need more time and a different talk, and I can do that. Right. But the idea, I can explain you, the idea is the following. I also in my paper, in the end, I try to present my argument as a reply to Hintika. In his paper of 2011, I think, called "What is Axiomatic Method?" And in this paper, he presents what I think is indeed more or less like classical Hilbertian view of early Hilbert. So he also takes this strongly semantic view. He also says principal inference is semantic consequences, not anything else. And then, of course, he discusses how this relates to, possible experience, to empirical science. But he says something like that, and that I think close to what Hilbert had in mind, that we had all kind of, intuitions, experiences, and with this machinery, we kind of put things in order, right? So we design our axiomatic systems in a way that they would have the intended models, right? And possibly minimum unintended models, something like this, right? And I think what is not wrong, but say insufficient and not sufficiently close to really scientific purposes in this story. And this is exactly the following point, that in physics, for example, think about how we apply, say, Newtonian mechanics for producing mathematical model of an orbit or a planet or something, right? Or just we throw it all and have a parabola here, right? What we are doing here? It's not that just we have equations and so on. So my claim is that we use kind of constructive procedures. We not just put these things, we have some stock of them, right? And then we have some proposition, formal proposition from our theory, and which we look for in the stock for thing which satisfies in tactical sense of our proposition. It's not like that. We have kind of constructive procedure, right? We produce these things by kind of constructive procedures. You see? And that's exactly what is missing in this axiomatic method, but what is supplied by in Hart in the form of these rules when they serve not as an inference rules or proposition level, but when they serve on this higher level. No, it's a project. Well, I don't know how to do physics with that. Maybe Urs Schreiber knows better. But that's somehow a project. You see that you apply this for, if you like, constructing your models, right? Important things that complicated models, they are not that, and that's what I believe. It's my really Cassirer points to, right? that replace what he calls object, replaced by model, right? And interesting model in science, they have the structure, and this is not just structure propositions about them, but it's structure of how they built from simpler elements to something more complicated. You see, so we need a formal, tool for treating this. That's what I think. Homotopy type theory, perhaps. Of course, the whole project depends on what Vygotsky called univariate foundation, right? So the idea is somehow to build a lot of mathematics on this language, and then kind of mathematics that could be used in physics and science. But I agree, of course, it needs further discussion.
But on the outdated view, in fact, the kind of view that you defend on model is very close to what I heard René Guittard defending. I mean, each time he wants to talk about model and he wants to emphasize about the role of category and so on. He says what we are doing is giving models of mathematics inside of mathematics in a way which is very similar, according to him, to what we do in physics. This is what he claimed.
Yeah, but it's an analogy. It's not about.
I think it's an analogy also here. I mean, it's not. I don't think Cassirer is claiming that really. I don't think Cassirer is claiming that mathematics is an empirical science. It's just the fact that there is a heuristic of mathematics which work, and I mean, I don't think Cassirer think that mathematics is an empirical science.
No, I think it's a transcendental.
Yes. Yeah.
About experience.
Yeah, but this is the same claim by Guittard. It's because it's some kind of it's a way to describe reality. So then it's an activity of modeling, and then you can give models inside of mathematics in the same way that we do model outside, because it's completely homogeneous. I mean, there is no discrepancy between what we do in mathematics and what we do when we mathematize reality. And he said that very often time, to the big surprise to some people in the audience, but just to say that, and he says that on the ground of a certain practice of categorical logic. There is a paper which is called What is Logic in a Category? You know this paper? Yeah. And he claimed this about foundation and so on, and this kind of thing. So I just think that this is like, I mean, it's very broad and so on, but it's not completely crazy. I mean, I heard many people saying, and even Lowe, when he was asked about the origin of, you didn't talk about this, but he was asked about the origin of Topos theory, he emphasized the fact that it came from physics and from the fact that he wanted to axiomatize continuum mechanics because of Truesdale and so on. And he says, no, it doesn't come from logic and so on. I was interested to logic because I wanted to do physics and so on, and synthetic differential geometry. So, it's an analogy, it's something a little bit methodological to finish with, but it's not so, I mean...
I think you may say the same about Hilbert, actually, that his motivation was very much in physics. It was not like logic.
Yes, but there's something also which I find a little bit confusing, is that you use, and in the discussion it appears Hilbert as a name, but you have many different things in Hilbert. So you have the formal system à la Hilbert, which is something, and then you have the axiomatic method according to Hilbert, which is another thing. And I think it's important because what you want to fight, I don't know if you're right, but what you want to fight is clearly axiomatic system à la Hilbert. If whether or not this was, for example, the ground for kind of Bourbaki style is not clear to me. It's not clear to me at all, and this is a discussion we had with Renaud Charlet for a long time. That is to say, we have to be very careful because axiomatization, as used by Bourbakists, was not meant as a way to do some kind of logic and so on. When they describe it, it's a way to, and this is very Russellian, it's a way to sharpen the proper concept of a domain. And that has nothing to do with the way that you conceive if axiomatic gives statements or about something and so on. It's the way that you conceive the role of axiomatization. And on that view, I'm not so sure that categorical logic, elementary topos, and so on, are not in the heritage of Hilbert. I mean, it's very conceptual. Well, of course, the ideology is Hegelian and so on. Why not? I mean, they do what they want, they take the philosophy they want. But this idea that you find everywhere now, that you have to sharpen, you have to find the proper axiom because it's a way to sharpen the concept, is exactly what Bourbaki's manifesto, the architecture of mathematics, claim as being the typical way of the. But of course, it's not axiomatic system à la Hilbert, which is clearly a place where Bourbaki failed. Not failed. I mean, they were clumsy, did not work, and they knew it. But then when you look at the Bourbaki's mathematics, that means the kind of axiomatization that they did, just think of, I don't know, a uniform structure axiomatized by André Weil. It's a way to sharpen a domain that was not discovered before. And you say, okay, this is not metric space, this is not topologic space, this is in between, and because I can sharpen the proper axiom that I need to do, that I need in order to derive part. But it's not formal theory. They don't do formal derivation at all. No. They don't know model theory, they don't know all of this. And you have this in Hilbert also. But for me, it's two different things. I mean, I have the impression that it's the kind of axiomatic that you find in categorical category theory is very like conceptual mathematics. Conceptual mathematics.
But first of all, what, as you put it, I want to fight, I just put it here, right? There's two things. And I think these two things, they apply both through all Hilbert career. Of course, there is differences, but I think this applies both since 1899 to this later project. They are not so specific, right?
No, but I'm not talking about Hilbert the guy. I'm talking about the way that people imitate from Hilbert. Right. So you have the logic, which is here. This is the logic, the logical side. That was used mainly by logicians. But when you look at the way that differential geometry was axiomatized by, or look at the way that Hermann Weyl axiomatized complex analysis, and the way that you will just invent the axioms for manifolds, bidimensional manifolds with the role of paper.
But you're absolutely right that there are many things going under the name of axiomatic method, exactly.
But mainly in math, what I'm describing in mathematics in the 20th century is the vast majority. It's the vast majority. The way that we axiomatize theory, it's like we do in category theory, according to me.
But talking about Bourbaki, I read this architecture by doing mathematics, right? And I think it's, in a sense, it applies what you just described, but I think they're kind of confused. They in practically speaking, so to speak, right? They indeed do many interesting things, but conceptually, I don't think that they have any, say, alternative idea of axiomatization, alternative to Hilbert. Because, for example, what Dieudonné writes at the beginning of this architecture of mathematics, he said, okay, we put axiom and we derive formally stuff from them. And he gives example, which in my view is kind of, how to say, non-representative at all. Because he says, okay, we give axioms for group and derive that the unit of group is unique, right? And that, of course, is very atypical, because what group theory a la Bourbaki is basically a model theory of this little three axioms, right? It's without talking about every, say, group up to isomorphism is, so to speak, particular model of this axiom. So just to formulate something like Lagrange theorem, it's a kind of model theoretic theorem. Actually, it is not derivable from axiom as itself, right? So it's an issue of different models. You cannot otherwise talk about subgroup of a group, right? Because it's kind of model theoretic construction subgroup.
No, I agree with this. But this is the ideological part of Bourbaki, because when you look at the way that they refer to the kind of axiomatics that they like when they say Fréchet. Okay, Fréchet is one of their examples, or Borel and Lebesgue on measure theory. When you look at this kind of axiomatics, it doesn't work this way at all. This is really a way to describe the basic concept. I mean, you want to have the most general concept for metrical space, and you invent the object. I mean, it's a way to it's object centered. Yeah. And from what I learned from Sébastien Gandon, this is exactly Russell's point of view. So in this way, I think there are two stories going parallel. This is what I would say. One is the logical story, and you have a lot of question about what is a formal system, what is logic, and so on. And it's very complicated because you have all this question of proof theory, the many different ways. But then on the side of mathematics, it's much more closer to what we are doing today. It's just as if we take out the glass of some logical view on mathematics and be more pluralist about logic and say, okay, it's not one way to I think that what we see is that this is not a good description of axiomatic theory in mathematics. This is what we see today, but that was always true. That was always true. We see it today. We see it today, maybe better than other days. Would you agree with that? Because it's important for your story about axiomatization, because your story can be, okay, no, we did another kind of axiomatic theory until Topos theory and Homotopy Type theory, and now we have a new way to axiomatize.
Absolutely.
Yeah.
Even in the book I included this chapter.
Yes.
Of course. But I think what I look at my project and everybody else, what should be the because of course it was never in practice, but I think we need kind of clear alternative idea, right? Because people may not follow that, but without having any alternative clear idea that maybe also not exactly correspond. But
no, that's what you're right.
That's
you look at Bourbaki, the kind of ideas that they are very confused. Then you're right that when you look at Bourbaki, their ideas of what you are doing is completely confused because they are mixing both. That's clear. Or for example, the example that you gave of Tarski is very nice because in one way you have Tarski doing logic, in another way he is doing universal algebra. And this is just after the Stone theorem and so on, so we see the parallel, and it's purely axiomatic method. The trend of universal algebra, it's purely axiomatic method. And you see the deep parallel between topology and algebra, and we transfer immediately to logic. Tarski sees it, develops it, but there is no deep connection between the two. It's too, and you're right, that it's only, and it's too bad that Simon is not here because something that I would like to, Simon de Camps, because he works on universal algebra, and something that I would like to understand is the relationship of all of this new axiomatic with universal algebra. Because Lowell said that when he created the first the elementary, no, the first thing that you presented on the category of sets, he went to people in the universal algebra because he was sure that they will understand and discuss with him. And he said, but strangely enough, they did not understand. He says that in the preface to the new edition of his PhD. He says, I wrote these for people in the universal algebra because you have all the subobject classifier, these kind of things, which are just the generalization of lattices of subobjects and so on. It's very. And he says, and I went to them and they did not understand me. So it's interesting because there is, in a way, a certain continuity in which you see this parallel between topology, logic, and algebra, which is really the idea of universal algebra. But there was a shift, and we have to understand which shift it was exactly, and it's not so clear to me what happened. And we did not find exactly what happened. How is it that people, because universal algebra, starting for this moment, started to be a very small, particular discipline with a few. Now people are talking about universal algebra, but in category theory, mainly. But at that point, there was a book on universal algebra. I don't remember the
Course. I know course.
No, what? You know this book which is called Universal Algebra?
Whitehead, of course, wrote.
No, not Whitehead. It's another story. It has nothing to do with this kind of universal algebra. But there was a big textbook in the 60s, but nobody worked in this. Now it's a very specific field, very small field. So there's something interesting on the history of axiomatic method and this parallel between the logic, the history in logic and the history in algebra, in geometry, and so on. And Renaud did a lot of work on this, Renaud Chanlet. You should talk with him. Renaud Chanlet. Yeah. Because he worked, for example, on the axiomatization of differential geometry.
Yeah, I looked a little bit. I looked on Veblen, because that was Veblen's
Veblen and Whitehead.
The dissertation.
Yeah.
And that is rather because he wants to apply this Hilbert's say, soft method, right, of earlier. But then at a certain point he stops, he just gives, it's very, very interesting.
But the common, I mean, share of Russell and Bourbaki is that mathematics is a conceptual discipline.
Yes, that's why
I think that if you want to follow that suggestion, you have to see mathematics as a kind of conceptual autonomous discipline, and it has nothing to do with applying mathematics to experience and thinking objects and sense. I think it's hardly compatible.
No, but that will be what will be new. What will be new nowadays, the point of view à la guitare, is to say what is precisely new is that we still keep this idea it's a conceptual discipline.
And on top of that, we formalize experience and physics.
No, we don't believe, we are not Platonists anymore, we don't believe that there is a world of concept somewhere that we have to find. It's some kind like an empirical science in which we have to modelize this concept, and they can move, they can change. We don't believe that there is one thing. This is what he would say. He would say that, okay, we've tried to find the proper conceptual framework for everything in mathematics, but it's not the way it works. We have now many, that's true.
In that sense, every mathematician is an empiricist. I mean, we have to try to organize things in different ways, and there are many ways to do that, and we try to find the best way, but it's a matter of...
But which is the experience?
But it has nothing to do with what Cassirer has in mind.
No, it has to do, because in this, say, standard conception, okay, people, rather why mathematicians even today, a lot of mathematical, not all of mathematical work, but a lot of mathematical work kind of, you know, motivated or focused on something which can be used in physics. Not immediately. No, I think it's pretty much. No, okay, that's sociological claim. That's not important. But still, the usual response, right? What Hilbert, what Hilti later, it's something like that. That look, just scientists have some mysterious, I don't know, capacity, right, to develop mathematics exactly in such a form which can be useful somehow, right? And so this sphere of how it works is left to something, I don't know, cognitive science or psychology, so it's somehow excluded from anything like logic or say formal mathematics. And that's, I think, it's just not justified, because if we have this constructive part, we can understand that. Now take a simple example, historical example of Euclidean geometry, right? If I'm right that it is not propositional theory, it's a lot about constructing things, like so problems, perhaps at the central, not theorems, right? And so that gives us a tool for kind of constructing the world around us, developing from simple elements. We have rules, we have simple elements like circle and line, right, ruler and compass, and we have rules how we plan it. Maybe not fully formalized in Euclid, but we have that. And that allows us to use this geometrical theory in, I don't know, physics, optics, engineering, very successfully, whatnot. So if we wouldn't have this, if it would only a list of theorems following from axioms, we couldn't do this. That's kind of... So in a sense, it's diminishing this mystery of intuition of how scientists, make mathematics exactly useful for physics. But they need a separate issue, of course.
Other questions? Remarks?
I have a very little question, which is not directly linked to this whole debate. But you were, in some sense, proposing not in a very explicit way, but constantly logic to geometry. And I would have thought about like logic and maths, but your field in maths, to oppose to the logical view, is specifically geometry. Is there a reason for that, or you could also put their arithmetic, for example, arithmetic as not being able to be accounted for with logic and giving also some internal logic to it. Do you have a position on that, or?
No, for me it's also kind of open question. I just kind of looked at least in history of axiomatization. Geometry is also kind of central, right? And that perhaps, no, I don't know a good answer, but I think it's a good question.
But it's standard to
exactly.
believe that arithmetic is closer to logic than geometry.
Of course.
No, basically what I have some...
Which I think is false,
but historically speaking,
it was the field to conquer first from logic to build everything.
No, what I do think about this, it's very preliminary thought, but something like this, that I still think this we say totally outdated, but something like geometrical intuition. Right? And I think I argue in different places that it's, I think, of course, applied to modern geometry as well as Euclid geometry. It's kind of beginning 20th century that we should forget about intuitions that does not correspond to practice at least. But then there is the following issue. If we do kind of symbolic calculations, right? Of course we do use intuitions and that in Hilbert acknowledged in the form of these symbols. So we are doing this combinatoric of symbols, and one possible epistemic gain is this kind of a problematic intuition, unlike, I don't know, infinite parallels or infinite, things like this. But further argument, so in a sense, at least that was Hilbert thinking about that. In one place he distinguished between ideal and real objects and mathematics. So the only real objects would be these symbols, letters, and they are object for this meter mathematics, right? And all the rest are ideal, right? And so I think that it's just too impoverishing, so-called. Of course, it's important part of mathematics, the symbolic calculation. It's no question of giving it up. And perhaps with computer and stuff we have again something different. But I also think that something like geometrical intuition, which is less concrete, right? That is translatable into the symbolic stuff through what we call interpretation, like in homotopy theory. In that respect, it's a very good example. It also plays a kind of similar role. And so there is no reason give it up with the pretext that we invented non-Euclidean geometry, you see. So in that sense, it still may provide perhaps also kind of link to experience and physics. I know that kind of sounds very outdated, but I think it's still kind of defensible and revivable in some new context. So in that sense, I kind of neoclassical project for science.
But in any way, the opposition between logic and geometry was in the lower slide, the code that you gave. It's the way that you presented it.
Yeah, of course, it has been like
say opposite.
Yeah.
Logic and geometry are two opposite that.
It has been a leitmotif of the 20th century, but maybe that applies for broader scope, like mathematics at all, and logic instead of geometry as in geometrical intuition, and I don't know, something like an abstract dealing with symbols, in which arithmetic should be. Because even from a Kantian point of view, arithmetic makes part of the intuition, and the idea that arithmetic doesn't belong to intuition is something that Frege turns around. But from a Kantian point of view, it's geometry and arithmetic. It's time and space in some sense. So, but even if you go out from the Kantian framework, I mean, there are a lot of arithmetical properties, like I know the Riemann hypothesis, that would be very difficult to just attribute to a logical
in the homotopy type
of a system.
No, one develops arithmetic both in Topos setting, right, in the natural logic and in homotopy types. Actually, arithmetic, I looked at this recently in homotopy type setting. Arithmetic is kind of very standard, it's piano-like.
Yeah, exactly.
So, in a sense, it's too poor because then you prove something like 2 times 2 equals 4. That will be definitional equality in homotopy type. So
yeah, but I don't know. I've never seen like a logical treatment of higher arithmetic in this sense.
But don't forget that in the 20th century there were some results in Diophantine problems that were solved by logic as early as the 30s. So it was very. I mean, it was not based just on an ideology. I mean,
no, of course.
There are strange results in which you can show that if you have a higher order cardinals, you can solve some type of Diophantine equation. So why will it be the case? And you have no result like this in geometry, to my knowledge. You have nothing telling you that you can solve any geometrical conjecture by adding. So it's not so. It's not just the fact that arithmetic is close to logic because you can derive the axioms. And there are results in which you have, and even today. I mean, this is what we heard in John Malwich's talk. I mean, one of the main examples where model theory is powerful is higher arithmetic. When it applied into mathematics, this is exactly where it's you have this, but you have also geometry with algebraic geometry. It's a very specific topic, but so you have a connection, which is. But anyway, in the 60s, what was surprising is to have geometrical method coming back into logic. It was more on this side, because at first there is no relationship between sheaves and logic. At first sight.
It's interesting thing, of course. Look, say, if we may say in beginning 20th century, these logical methods really allowed to sort out things in geometry, to clarify things in geometry. I think it's not in a very big degree, but we may find that in some cases when that happened. But I think with Martin type theory, just exactly the other way around. It's not like in Topos, because there was something in these higher identity types, and the structure, which in a sense was there, but it was ununderstood. And that was complicated, we may say, combinatorial structure, which was untreatable on this by purely combinatorial, standard combinatorial methods. On the symbolic level, was just untreatable. Nobody understood how it works. And in that sense, it was greatly clarified, so we now understand it much better through this homotopical interpretation. So in that sense, it's just geometry which really serves for understanding logic, if you like, or at least syntax. You see?
I think we have to stop now.
Thank you.
Thank you very much.